Hello. Okay. Great. Nice. Okay. Hi everyone. Great. So, quick introduction. My name is Dharam Thakkar. I'm working with AWS as an enterprise solutions architect, managing the FSI customers, financial services customers, which includes banks and many other financial entities like capital markets, insurance domain, the NBFCs, mutual funds, etc. So that's what I take care of. This quick introduction. Fine. So um, today, before we jump into the session, this session is more about doing a deep dive into the event-driven architecture on AWS, where we'll be shifting gears from basic to medium level to slowly advanced architecture stages. I'm sure that you all may not be very well versed with all the event-driven services available in AWS. So I'm going to start with the basics for sure. But before we start, can someone tell me about all the messaging services available in AWS for achieving point-to-point integration? Does anyone know? Point-to-point integration. Yes, please. Okay, one. Anything else apart from that? Sorry? Amazon MQ, that's a good one. Anything else? That's part of the Amazon MQ only, agree? Okay, that's what you want to learn today. A quick, little bit more complex question. Does anyone know the throughput which Amazon SQS offers now as of today? Amazon SQS, I think the first service which AWS introduced. Do you know the throughput which is offered by SQS today? Anyone? 300 messages per second if you do the singular one by one messages. And if you go with the batching, then it offers 10 messages in a batch, so 3000 messages per second. There was one more new mode added into SQS, which is called high throughput mode, which offers up to 70,000 messages per second throughput with Amazon SQS. Just for introduction. Let's switch the gears. So what we are going to cover today is primarily two things. One is the enterprise integration patterns, where we'll be covering various different methodology to connect the services. And then we'll slowly switch our gears and go with the advanced level of enterprise event architecture. Perfect. So I'm going to use this word coupling a lot during this. So I just want to get all of us onto the same page that what does coupling mean. Right? So normally coupling simply means dependency. You probably may rely on your girlfriend. I rely on my wife. Once the baby comes, we rely on our baby, right? So in a software world, coupling means how two different services are interconnected or relied or dependent on each other. The more the level of coupling, more it is hard to replace each other. And if you want to decouple them, you have to introduce someone in middle, right? As an example, someone mentioned about queue. What is queue? You're trying to decouple two things, right? So that you can reduce the dependency between these two services. And if you have to really replace one part, you can easily do that. That's what we say decouple. But the moment you introduce this decoupling, there's some intermediary in between. It means now there's a design time cost because you're putting someone in the middle. Plus there's a runtime cost as well because now latency is not going to be exactly same as what you get with the sync service or the coupled service. Coupling means you're calling an API, you're calling the web service directly. There's no baggage. But the moment you are trying to decouple something, you're going to put something in the middle. That you take care of this responsibility, I'm not going to do that. So that means there's a cost involved in terms of the build time or the design time, plus runtime cost is also involved, which we are going to see and look at when we go to that part actually. But there are multiple dimensions of this coupling which I want all of you to be aware of. Because when you are really designing a system, there are different angles which come into play. Which technology choices you are making. which kind of formats you are putting on. Like someone may use RPC, XML, binary, Avro, Proto, but you know the implication of this format? Maybe you say that, look, I want to design a distributed system, but I know that JSON is a universal standard and I'm going to use that so that I don't have to do unnecessary transformations when my message moves from one system to other system. That's how you're trying to reduce the coupling. The way you are calling your services is directly by invoking the API or by the web service. No, I don't want that temporal coupling. I want that I put a message on queue and then someone takes it from the queue. So it's also a type of dimension which we call. Similarly, one more thing which you may have seen is that a lot of time you write lots of if then else statement. If like this, then go to here. Then go to here. Else go to here. Which is also a type of location coupling. Like, look, you are maintaining a logic of where to send a message, why you should be. There is a component called event bus. You can really decouple your services like that way. So this is how we are going to switch the gears, but I just want to make sure that all of you understand the dimensions of this coupling when you are designing a multi-modular system which is really decoupled and works in a way that the other part is easily changeable, replaceable with something else. That's how we really design the distributed system, right? So let's move and switch the gear to the first model. It's very simple. I'm sure you all of you have used that. There is sender, there is receiver. You call a web service, you call an API, that guy responds to you, and that's done. Very simple synchronous request response model. We have used a lot of time during our college life. We're even now using web services part. What are the advantages here? Of course, it's very simple. Yeah. It's low latency because there's no baggage involved, there's no transformation involved. You're simply invoking the API, you're simply calling the web service, you get a response, you're done. If that receiver is not available, you immediately come to know that something is down and you're going to fail fast. What to do next if something is not available? So there are some advantages. It's simple, there is low latency because there is no baggage involved, there's no middleman involved, and you can fail fast. But of course, we know that this approach has lots of disadvantages too. So, what if receiver has failed, right? So that means if receiver is failed and sender has no way, it's gonna fail as well. Shadi karni hai to both parties has to be there, husband and wife. Then only things gonna work like same thing. Sender and receiver both has to be there for synchronous request response model to work. If receiver is down, you're going to fail. Of course, you're going to fail fast, but you are going to fail. You have to either plan and design an alternate path, or you are simply going to retrack, back of exponential retrack, until the receiver comes online. The other disadvantage, if the number of senders are increasing and still the receiver is same, so there's a burst of traffic, there's a thunderbird, right, in terms of the request rate. And receiver is really not designed to catch up with that number of requests which you are sending to receiver. It's going to go down. And then what's going to happen is that every single sender is still trying to send and hit you the request. So there's already a backlog of requests created. And when receiver comes online, it has to still deal with that recovery which is still pending at the sender side, right? So there are receiver failure. If receiver goes down, you are in trouble. There is a threshold. It means if receiver is hitting a burst of requests and still sender are increasing, there is a throttling kind of an issue at the receiver side. So this model is suitable for something, but it's not suitable for nowadays. So wherever there is a possibility to decouple things and introduce a middleman, you should do that. Ultimately, that's an idea. You should be aware of that when you are going with the web services. It's not always to think about the REST-based web services or GraphQL-based web services. There are lots of async options as well available. Like someone explained the recently serverless coffee shop. Do you really think that the banking transaction or serverless coffee ordering or the insurance buying, all these workflows which you are seeing on your core banking applications, they are designed in a synchronous way? When you make a UPI payment, what do you think? Is that a synchronous service? No. It's not a synchronous service, right? So that's what the design angle which I want you to think about when you are designing a highly scalable, reliable, distributed system. This coupling dimensions you should always think about. That's the idea to demonstrate the synchronous request response model. So what's the way to solve this problem? Of course, some intermediary like a queue, which is nothing but some sort of buffering mechanism, right? That helps us to decrease the temporal coupling. Temporal coupling means now I'm putting some intermediary. I'm not directly dependent on you. If you want me, talk to my secretary first. Then the secretary will plan with me, and that's how things is gonna work like, right? So queue is just an intermediary, it's a buffering mechanism. Now what are the advantages? Even though your receiver is down, you are not impacted. You are still sending messages to queue, queue is buffering your messages. And whenever receiver comes up, again, even though your sender is hitting with n number of messages, the receiver can say that, look, I can only process 100 messages per second, and I will control the consumption rate. SQS is pull-based or push-based? Can someone tell me about that? Amazon SQS is pull-based or push-based? Sorry? Pull-based. You pull messages from SQS, and that's how you control your consumption rate. Maybe other brokers you might have seen about JMS, AMQ, we will cover that. But SQS is pull-based. You pull messages, you process the messages, and once the processing is successful, you send an acknowledgement back to queue and remove a message from the queue. Right? That's how you work with the Amazon SQS. So receiver has full control over the consumption rate. That's the idea. Now, most of the time you see that even though receiver has a control, even though this pattern is going to solve the problem by putting some intermediary, there might be bug in receiver processing transactions. And what you want to do is that always there is a best practice. Even in AWS there are n number of services which offers a DLQ. Something fails and send it to DLQ, dead letter queue, right? Similarly, after processing 3 times, 4 times, so maybe depending on the timeout which you have set, that if receiver is not able to process a message within 60 seconds, I want to mark that transaction as failed, go to DLQ. Why DLQ? Because I can't take a risk to lose that message. I always want a persistent way to save a failed transaction, so that either at a particular time interval I can pull that messages back, or someone else, maybe let's say failure listener, there's a component which listens to the DLQ or any other queue, and any messages which has failed, it picks up from there and processes that. So there's a DLQ, it's always the best practice that when you're working with asynchronous architecture, always have a DLQ in mind. So now let's do the same model, but think about one receiver is not good enough. Because I'm receiving the messages like 10,000 messages per second, there are n number of senders. So what would you do? You will say that, okay, I will horizontally scale my receiver. That's a good thing which you can do with the queue. But what this pattern is called? Competing consumer pattern. All the consumers are competing with each other to pull the message from the queue. That means you can only get a one message, no one else can get it, right? One message can only be received by one receiver. Once you get it, no one else has the visibility to that. You will process it, you will consume it. If everything is fine, you will commit it. If it's not fine, you will fail, then it will go back to the queue. If it goes back to the queue, then someone else can take it. But while the control is with you, no one else can take it. So this pattern is called the competing consumers pattern, right? Where you can have a multiple receivers who are fighting for the same queue, so that you can increase your overall throughput. Because I have n number of messages coming at great speed. One receiver is sure not good enough, right? So you would like to have a horizontal scaling for your receiver, so that you can increase your consumption rate. I have lots of diagrams to grab you these concepts very easily. So be with me. We will so change gears to the little bit more advanced mode, but I just want to make sure that we all are on the same page in terms of the concepts part, right? So, perfect. Now, what's the disadvantages of this approach? Because everything has a pros and cons. In synchronous model, when you are processing a request, you know that the response is for this request only. But in the asynchronous, you need something to correlate that this response is for which request. It means there's an extra dependency on correlation ID, right? So that's what response correlation is required if you're going with this some kind of intermediary part. Other thing is that if senders are kind of thunderbirding your queue and sending lots of messages, somehow your receiver goes down. When it comes back online, what's going to happen is that anything which is pending so far, they are the first one. So it means it's going to first clear the backlog before it can process the new messages, right? So backlog recovery is kind of a problem. Of course, there is a way to solve this problem, and what you are going to do is that you may probably decide to put those backlog messages on a different queue. That look, hey receiver, when you come online, check the timestamp of the message. If it is older than 2 minutes, you know that it's not the latest message. Throw it to some other queue. Because you want to give the first priority to the latest transactions, right? So of course there's a way to solve this problem, but it's a problem which I want to highlight. You can always check the timestamp and put that back onto the different queue. And third thing is the fairness. Say as an example, there are 3 senders, but one of the sender is sending 10 messages in comparison to the first one which are sending 2 messages or 3 messages per second. But see, receiver has no knowledge about which sender is sending more messages. It will simply take a message, process it from whichever sender it is coming from. So there is a fairness issue as well, that one sender is getting more chance compared to other sender. Of course, there is a way to resolve this problem as well. If any sender is sending a lot many messages than any other sender, what you can do is that you can have a dedicated separate queue for that sender, so that you can't face so that you don't face this fairness issue. Otherwise, the other senders will be running a bit slow than this sender, right? So that's kind of the one of the known problem, and there is a way as well to solve that. But we should be aware of that, when to use which kind of methodology to solve an issue. Perfect. So let's switch the gear and go to the now we know that we just discussed about the queue and what's the service. We also discussed Amazon SQS is a service which is fully managed, serverless, distributed messaging queue in AWS. It offers 2 flavors, FIFO and standard. FIFO queue, I just told you about the performance, 300 messages per second. If you are going with the single messages. If you are going with batch, then 3000 messages per second. And if you are going with the high throughput mode, which is very latest, I guess 3 to 4 months it has been introduced, 70,000 messages per second with SQS, which is a lot. And it also comes up with the DLQ support too, which you are looking for when you are going with some sort of intermediary, right, in a point-to-point pattern. So all these options are satisfied. Okay, now let's go to the Amazon MQ. Now someone already mentioned about that Amazon MQ is also a point-to-point service. But doesn't even know that what kind of protocol does Amazon MQ support? AMQP and JMS. Traditional protocols, JMS and AMQP. It comes up with the 2 variants, right? RabbitMQ or Apache ActiveMQ. Both of them are offered to as a fully managed service, so that you can only do differentiated things. You don't have to worry about how to scale my brokers. And by the way, this is a push-based system. It's not a pull-based system when you go with the Amazon MQ versus Amazon SQS, which is a pull-based system. Time is running so fast. Okay, so let's just do recap what we learned about so far. Point-to-point Amazon SQS, but not always you need a point-to-point model. If you say that my message should be consumed by more than 1 subscriber, you need something like topic, right? And that's what we are going to do quickly. So topic is another way to introduce an intermediary, where I'm saying that I need a fan-out pattern. I don't want only 1 subscriber to consume my message, but I want a copy of my message to go to n number of subscribers. And then you will put up topic. Topic will send a message to the dedicated queue or your subscription part, right? The performance point of view, it's very much similar to the SQS, and we have a service called Amazon SNS to do the same thing in AWS. So SQS, SNS, point to point, fan out model. If you want to go for the push based model, then you have an Amazon MQ, which we also described about, for the JMS and AMQP protocol. Now, there is one more thing, AWS IoT Core. Has anyone used that IoT Core? It's mainly for the MQTT protocol over WebSocket or IoT devices. But it's also a serverless messaging service similar to what we described so far. Okay, now we're going to talk about the router. So think about like this way. You want to send blue messages to blue channel, green messages to green channel using queue. Some sort of intermediary in between so that you can achieve the decoupling. But look, your sender is managing the logic of where to send the message to, which is not good. Why? Because that introduces a location coupling. Some of your component has a responsibility to manage that logic on where to send a message, right? So we have to reduce that. We need someone else, so some more intermediary apart from queue, who can take care of how to send the message, where to send the message, right? So we have to introduce one more intermediary in between that so that we can remove the logic from the sender. Now if it's just a two channel, it's still okay. You can manage that. But what if that increases to multi-channels, right? Sender becomes a lot more complex. So many then else statement in your logic. You decide where to send a message and how to route the message, which is not a good idea. Even though this pattern works, but ultimately you are increasing a lot many location coupling in your logic. So to reduce that, you will go to some sort of router that look, I know only event bus. I'm going to send a message to you. You take care of how to route the message to somewhere else. So that's what you see here. There's an event bus, and then there are two rules determined based on the event bus. If it's blue, then send to blue channel, and green, then send to green channel. And that event bus in AWS is nothing but Amazon Event Bridge. How many of you are using Amazon Event Bridge? Oh, quite a few. That's good. Okay, so idea is to again reduce the dependency, reduce the coupling, and make your senders and receivers still transparent about who is routing the message. They are still sending message to event bus, receiver is still consuming message from the event bus. It's remaining as it is, right? No changes. Now, as I mentioned, that Amazon Event Bridge is fully managed pay-as-you-go service, which has 4 stages. You can ingest messages from n number of AWS services, or SaaS partners, or your own microservices, or Confluent Kafka, or self-managed Kafka, and many other things from where you can ingest your events, messages, right? Then you write a rule engine, because it's some sort of event matching engine that, if rule is matching to this event, send it to here. If it's matching to that event, send it to green channel. So you write your rules here, which helps you to achieve the router path. Also, it supports schema registry too, just like a Kafka supports schema registry. And then you send it to the target service, which could be Lambda, SNS, SQS, and many 70 or 80 plus services are supported in Amazon Event Bridge as a target services, right? Okay, so here is a sample event. So normally with any Amazon Event Bridge event, there are two flavors, there are two parts. One is called the detail section, where it contains the data part, and the other is called the metadata section. Now, in the data is your actual data, which is your event, like order or patients or employee or customer created, any sort of things goes into the data. And then you define a rule on top of that. Here what you see is that if my currency is AU or NZ, I want to accept that message and go to the SQS channel. So you see that the data part also contains currency is AU, My event matching rule also says that currency should be either AU or NZ. It supports not many such expressions. It could be the list like this way, it could be denial list, it could be the string prefix filter. So many expressive languages are supported in Amazon Event Bridge, and that's how event matching happens. And if event matches, then the rule engine will route that message to your desired target destination service, so that you don't care about writing and managing that logic, right? I'll take 5 more minutes, about to finish. So as I mentioned that the event bridge destinations are more than 70 plus, supported by AWS, where you can route your messages to once an event bridge rule is matched, right? Now, quickly introducing the event bridge pipe, which is really an interesting and innovative concept. Look, when you are consuming a message from SQS, you need an SQS client, you need an SNS client. If you are consuming a message from Kinesis, you need a Kinesis Consumer Library KCL. And so for whatever integration type you are writing, you need that library, you need that client to interact with. It means you have a responsibility to write that integration code. What if someone says that Eki pipe, there is only one pipe which you can use for your basin, for your toilet, for your bathroom, or for washing machine. Just use one pipe, and I will take care of how to hook that, how to integrate that with your channel, your source, how to filter the message, how to transform the message, and then send it to your destination. So to simplify that integration wiring, right? Instead of you managing a lot of code bases, different clients, that's where the Amazon Event Bridge pipe comes. So let's go to the pipe architecture quickly, right? So this is how. Again, it supports several sources. Just like I mentioned, washing machine, bathroom, toilet, washing machine. You just fit one pipe. That allows you to ingest a message from that source. You can filter it, you can enrich it, and then route it back to your destination. So pipe is a fascinating point-to-point integration technology. So think about if you want to consume a message from SQS, what you would do? You would write a Lambda function. That means you have to write a code, you have to deploy it, you have to do the performance monitoring for that. And then finally you will put message to something else. But instead of you writing the code, what if pipe can tell you that, look, you don't have to worry about how to deal with SQS. Just fit me, just create me. I will integrate with SQS queue, give me which SQS queue. And where do you want to send message to? That's all. So, you're not writing any code. You're not deploying. You don't have to worry about the performance monitoring and throughput testing. Pipe is able to help you with that end-to-end integration testing. Perfect. Just now quickly on the advanced architecture part, I know I'm running late, just 1 more minute. We discussed about this part. We are fitting a pipe between SQS and step function. You can do this with Lambda as well. But remember that then in that case, you know how to deal with SQS. You have to write that code base and you have to call the step function. Instead of that, now pipe is doing that work for you, which is an Amazon Event Bridge pipe for point-to-point integration technology. Same thing for Kinesis. I'm consuming a message from Kinesis. I have 2 pipes and I'm doing the filtering, I'm doing the enrichment, I'm doing the transformation and then sending it. Like there's a clickstream event on the website. One team is only interested for which all customers are interacting in this section. Other team is interested for analytics use case. So for both of them, you have different streams. And you want your event bridge to do that kind of routing for you, and that's how it works, as you can see it here, right? Using the point-to-point integration technology. Same thing for the self-managed Kafka or Confluent Cloud. You can consume the message and send it to various other things, like we show about the step function. You can trigger any API. If a message comes using Amazon Event Bridge pipe, you can even trigger an Amazon SageMaker pipeline for the real-time training purpose. Now switch to a little bit more advanced gear here. Now what you see is that the DynamoDB streams. This thing can be very well achieved using the Lambda part. But remember that you should be knowing about how to integrate with DynamoDB streams and how to call something else. It means you're writing the code. If you don't want to write a code, then go with the ready-made technology like this way. like an integration pipe using Amazon Event Bridge. Okay, and last thing, if you don't know about the Kafka, right? Kafka is also one of the very well-known technology. We are just skipping this part, but I just want to show you one quick architecture so that it's very clear to you. There's been one open source connector released by the Amazon Event Bridge, which says that now you don't even have to write a code to consume from Kafka and send it to Event Bridge. You can use Amazon Event Bridge Kafka connector, which is open source, which will help you to connect with the Kafka and send it to the Amazon Event Bridge. Once the message is on Amazon Event Bridge, it's your world. You can do anything which you want to do, like routing, filtering, transformation, where you want to send it, it's all up to you, right? So this connector helps you a lot. If you haven't played with that, it's a fascinating feature. It's called Amazon Event Bridge Kafka Connect Connector. It's an open source. Perfect. So this is what I wanted to talk about. Once the message is on Amazon Event Bridge, it can help you to trigger step function, Amazon SageMaker, put a message on Amazon SQ, or put it onto the Amazon API gateway. Or you say that, look, I want to call some third-party APIs once a message lands into Amazon Event Bridge. Everything is supported without you having to write a code. This is more important, without you having to write a code, because there is already a better tested, proven technology to do and help you with that. Plus all sorts of monitoring aspects are embedded into that. Perfect. So with that, I will take a pause, and I'm sorry that I'm late for this. But I just wanted to give you a flavor of all these things. Thank you so much. Okay.
Thank you so much, Mr. Dharam sir, for sharing your knowledge with us. And I would like everyone to please scan the QR code so that you can give your valuable feedback of this session. And I would like to request Mrs. Dimple Waghela ma'am to give a token of gratitude to Dharam Thakkar sir for doing such an innovative session. Give them a huge round of applause.